this one. Okay, looks okay. Okay, any question from this time? Well, I guess still go through this quickly. So yeah, this time we go over a lot of algorithms. Okay, go over 4 different quantum algorithms: Teochew algorithm, Teochew-Sa, Presley-Maroney, assignments. They have bigger and bigger separation between quantum query complexity and classical query complexity. But now we need to go back a little bit to midterm. As we say, we will have our midterm explanation today. Okay. Okay. Yeah. And yeah, as we said, we will do midterm explanation today. And before I do explanation, let's take a quick statistic about midterm. So this is a breakdown of our midterm score. Okay, and for problems you see that we have an average of 49 out of 120, and pretty big standard deviation of 30 points. So there are still people doing pretty good. And for the okay, so the problems, I think some of them are easier. You can get 70-80%, but I think there are particularly bad ones, like the second one and the fifth one. And well, the ninth one is a hard problem, so it's okay. But yeah, the seventh one is a little lower than expected, and the eighth one is also lower. But I think the most surprising is the second one. Okay. So I guess let's go to the most surprising one. I think we have a homework problem very similar to this, so I'm not sure why a lot of people just give up on doing the second problem, which is which is a pretty standard calculation of measurement. This is like the very first thing we talk about in quantum computation. But anyway. This one is about measurement, and we test you on 2 different measurements. First one is measurement on computational basis, and the second one is measurement with respect to those 2 measurement operators. Okay, and it should be pretty standard, but let's do this once again. And so computational basis, you just want to express everything in computational basis state and look up amplitude. And so this thing, okay, so let's try. Let's see if I can get the correct answer here. So 1 over square root 2 and the plus is 1 over square root 2 of 0 plus 1 and tensor 1. And we have minus I of minus tensor minus, so it's 1 over 2, 0 minus 1. 0 minus 1. Okay. And so this is really just you need to do calculation carefully. And let's say okay, so now the calculation is getting hard. Let's say we take out 1 over square root 2 on both sides. So we have 1 over 2, and the first one is 0, 1 plus 1, 1. And then the second one we have minus I over square root 2 of 0, 0 minus 0, 1 minus 1, 0 plus 1, 1. Okay. And finally we can collect all the all the terms. Okay, so for 0, 0, our coefficient is minus 2 square root 2 over I, and 0, 1, our coefficient is 1 over 2 of 1 plus I over square root 2, and 1, 0, the coefficient is just this term, so it's plus I over square root 2, and the last one is 1, 1. 1, 1, the coefficient is 1 over 2, and let's see, sorry, 1 over 2 of 1 minus, wait, yeah, 1 over 2 over 1 minus I over square root 2, okay, and yeah. And so those are the amplitude to the full computational basis state. And okay, so what do we want? So the post-measurement state, okay, so depends on how carefully you want to do this. So post-measurement state are going to be proportional to those two. And if you want to keep the phase, which technically you can do, then you need to divide those by the norm. Okay? So post-measurement state, if harder, then you need to keep the phase. And easy, then these four are the post-measurement state. And the probability is those amplitude square. So probability of this should be 1 over 8. And this one is 1 over 8 of, and the probability of this one, okay, so everything is 2 square root 2, right? So the, oh, okay. So that's 1 over 8, and okay, let's see if I do calculation correct. And this is 8 over, then square root 2 square plus 1 square, and this is 3. And this is 1 over 2. Okay, I do calculation wrong. Let's see. Oh, sorry, so this is 2 over square root 2. Okay, so this one is also 1 over 8. Okay. This is 1 over 8, and this is 3 over 8. Okay, so now the number checks. So they add together to 1. And if you want to phase, then yeah. And if you want to phase, then you divide the square root back. So for example, you divide the square root of 1 over 8 back, then you will get rid of this, and you get the post-measurement state minus I 0, 0. But I think we also give full credit if you just get 0, 0, etc. Okay, and yeah, you can also divide this back, and so you have the normalized of 1 plus I, and that should be like 1. Oh no, it's a square root plus I normalized, so it's like 3 over square root 2 plus I, something like that. Okay, and yeah, so that's the first one. I guess the numbers in the exam are not good, so there are a lot of heavy calculation. You need to be careful. But the second one should be a bit easier. Okay, so if you just do what I remember. Okay, so you have N1, N2, and you have the unnormalized state as like N1 plus, then this thing you can just do both calculation. So 1I minus I1, and the plus state is 1 over square root 2, 1, 1. And okay, so this is 2 over square root 2, and okay, and 1I is 1 plus I, and then 1 minus I. Okay, and so probability is this thing non-square, so that's 1 over 8 again, and okay, and then the non-square of 1 plus I plus the non-square of 1 minus I. So non-square of 1 plus I is 2, and this non-square is also 2. Okay. And so that's actually 1 over 2. Okay. And post-measurement state is, well, this thing normalized. Okay. And so we want to divide by square root 2, so normalized is yeah, normalized, then you get rid of 1 square root 2, so I think it's 1 over 2, then 1 plus I, and 1 minus I. Okay, and then N2 plus, okay, and N2 is so let's calculate Then n2, as we say, is identity minus, so let's calculate n2 first. So n2 equal to this thing, so it's 2002 minus 1/2 of 2002 minus n1. So it's 1/2 of, okay, so 2 minus 1 equal to 1, and you just change the location of the I. Okay? And n2 is this thing. And then, okay. And so maybe there is a bit confusing is we write n1 and n2 as a POB element because we write like n1 plus n2 equal to identity. But the completeness for measurement is like n1 dagger n1 plus n2 dagger n2 equal to 1, equal to identity. And this actually check out. So I guess we can try to check this. So this is pretty special. So we have n1 plus n2 equal to identity, but actually the completeness still checks. So let's say n1 dagger n1 equal to, so this thing, so 1/4, and so n1 dagger is actually equal to n1, okay? Because you swap those two and you do conjugation, then yeah, then you get the minus sign back to here. So it's 1i minus I1 and 1i minus I1. And that's 1/4 of, do I do this correct? Yeah, okay. So 1 and plus this I minus I is 1, so it's 2. And, okay. Wait, oh yeah. And so here we have 2i, and here we have minus 2i and 2. And so this is n1 dagger n1, and n2, as you see, you just swap the minus sign. So n2 dagger n2 is the same thing, but you have the minus sign here. So I guess that's still write down. So n1 dagger n1 is actually equal to n1. Okay. And oh yeah, this is the easier way to see this. It's 1/2 1i minus I1. So it is actually equal to n1. So we can do this because n1 and n2 are actually projectors. Okay. Yeah. So they're actually projector onto y plus and y minus. So n1 dagger n1 equal to n1 and m2 dagger m2 equal to m2. So projectors and some of them equal to identity. Okay. And anyway, so that's what n1 on plus, and n2 on plus is similar. Okay. So n2 on plus is 1/2 1 minus I1 1 over square root 2 1 1, and it's all the same thing, and you just swap the location of I and minus I. That's 1/2 square root 2 1 minus I 1 plus I. And yeah, so probability is still 1/2, and you normalize to similar thing. Just swap the location minus I. Okay. So yeah, it's a bit surprising to me that people don't know how to do measurement. So we will have another homework on measurement too. This week's problem set to give you more practice. Okay. Any question on how to do measurement calculation? So those are how you calculate probability and the post-measurement state. This is pretty basic. Okay. And I guess out of the surprising one, problem fact is really low is also surprising, kind of surprising to me, because I think it's pretty basic, although the calculation is really bad there. I didn't set up the number nicely, but let's go through other things first. Okay, so first one, I think people are doing pretty good on first one. I think only thing you get bad is like some calculation error. So like this thing, so remember, I keep talking about this, but I think some people still forget. So when you turn this y minus kt to y minus bra, so you turn into y minus bra, then then you need to do complex conjugation. Some people still forget it. Okay. and so it should be 1 over square root 2. So you turn a column vector to a row vector, and but here this minus I, it should become plus I and 1 over square root 2. Okay, so that's something people can get wrong. And then also there are a little trick on D and E, so you don't need to expand out everything because everything is in tensor product, so you only need to do then slot by slot. So for example, on the D one, then it's minus H1 and times y minus the y plus. Okay, and so this equal to minus so H1 turns this equal to another minus. I believe this answer is 1. And then y minus z, y plus. So z actually swap z plus and z minus, but that's just okay. Okay, the y minus here, and you can just read here. You apply z on here. So the first one got times plus 1, second one got a minus sign. So this minus I becomes minus I. So this y minus, and the y minus is a normalized state. So this is just 1. Okay. And yeah, and then similarly, the last one you calculate the inner product between. So last one is plus and y plus, and then the minus state, and so the minus state is actually a plus state, and but this plus and y plus is pretty ugly. You need to calculate like 1 over 2 and 1 I, and then the minus is a plus state, and then this thing is 1 over 2, 1 plus I, and plus state. Okay. Oh, well, we want matrix notation, so I need to expand this plus also. So 2 over square root 2, 1 plus I, and 1, 1. Okay, so that's the first one, second one, and the third one. Okay, so the third one you can do brute force calculation. You can write down the matrix for this explicitly and actually calculate the eigenvalue, but there's a way to cheat here. So remember we talked about block sphere, and we say everything that looks like this, V dot sigma, is like a poly, right? And so in particular, this kind of thing, they have like a poly, so the eigenvalues is plus minus 1. Okay, so what it tells you? They tell you that if a squared plus b, so if you have like some a tilde squared plus b tilde squared plus c tilde squared equal to 1, then the eigenvalue will be plus minus 1, right? And so we can cheat here. We can renormalize this matrix to have ABC some square equal to 1. So we just take all the square root of a squared plus b squared plus c squared, and so this thing, this operator equal to this renormalization factor, then times a tilde. Then times a tilde x plus b tilde y plus c tilde z with this thing, right? And so you know this part is just a number. This part is eigenvalue plus minus 1. So the total eigenvalue is plus minus this thing. Okay. So total eigenvalue is plus minus a squared plus b squared plus c squared. Okay. So that's how you can calculate this very fast on problem 3. Okay. And on problem 4, I think people are doing pretty good on problem 4. Okay. Yeah, problem 4. So it's a standard density matrix calculation. And okay, so we can calculate the density matrix. Y plus state. I believe y plus is actually n1, right? But yeah. So the projector onto y plus is actually n1. So we have 2 over 3 times this 1 over 2, this 1i minus i1, and plus so density matrix is this thing, and 1 over 3, and the projection onto 0 is just 1, 0, 0, 0. And so the number is actually nice here. Okay, and so the total number is okay. So I need to find some space, maybe here. Okay, and so the first register is 1 over 3 plus 1 over 3, 2 over 3. And then the other thing is just this 1 over 3. And I over 3, then minus I over 3, and 1 over 3. Okay, so that's a density matrix. And okay, and the expectation value of z, then you want to times z on this thing and take a trace. And I believe z will, okay, so z will depend on you multiply on before after, but anyway, z will take plus 1 on this 2 over 3 and minus 1 on this 1 over 3. And so when you take trace, you have 2 over 3 minus 1 over 3, so this should be 1 over 3. Hopefully I got the calculation wrong because it didn't check the answer. But anyway, so that's the idea. So it's 2 over 3 divided minus 1 over 3. That's the expectation value, trace rho z. Okay, so z equal to trace rho z. And then when you do computational basis measurement, okay, so that's you do projection onto 0 and projection onto 1. Okay, and so the outcome probability should be just this 2 over 3 and this 1 over 3. And the post measurement state will be this 1, 0, 0, 0 and 0, 0, 0, 1. Okay. And finally, then we have something that looks very like B but very different. On B, we are thinking Z as a Hermitian operator, and on D, we are thinking Z as a unitary operator. And yeah, so we say what's the state if you evolve this rho with Z? Then that's just, we say that should be Z rho Z. Okay, should be Z and, okay, Z rho Z dagger, but Z dagger equals to Z. Okay. And yeah, and that should just, okay, so one of them give you the, so I forgot which one is which, but z is multiplying minus 1. So one of them will give you a minus 1 on the last column, and one of them give you the minus 1 on the last row. So the end result is you will get a minus sign on the off-diagonal element and no change on the diagonal element. And so the result should just be, yeah, this thing with the minus sign move here. That should be the end result of D. Okay? Question? Not. Okay, and problem 5. Problem 5 is a lot of calculation. But because the number is a bit ugly. Okay, so first we want to normalize the state. I think people mostly get this? Probably a lot of people got 3 points, I think. So normalize, well, you want to calculate the inner product with itself. Okay, so we have a bad number here, so I just ask you to normalize this for me. Okay, so say tilde, say tilde. Okay, so a norm of psi is just this thing and taking square root. Okay, this is what we have here. So norm of psi equal to inner product with itself taking square root. And and last thing, and I guess there are multiple ways to do this. You can do this inner product with self, or you can just write everything computational basis state and calculate the coefficient. And write everything computational basis state, that's a little similar to this thing. But I guess let's try the inner product with itself. So anyway, inner product with itself equal to, so there are 4 terms, and those 2 terms, those 2, so this state and this state are normalized by itself. So we just have when the inner product with itself is got 1 and 2 of them is got 2, and then you have okay. So now it's actually tricky because it's y minus, I keep writing this wrong. Okay. Okay, so now we need to be a little careful because we have a complex number. So inner product is actually not equal to, is actually not symmetric. Okay. What I want to say is y minus 0 and y plus 1 and plus 0 and y minus and 1 y plus. And so those two turn out not the same, but they are complex conjugated to each other. Okay. So, and so this is actually 2 plus twice the real part of this thing, 0 y minus and 1 y plus. Okay. And anyway, okay, so let's calculate this. 2 times the real part of, and 0 on y minus is, okay, do I get this right? Okay, 0 on y minus is 1 over square root 2. Wait, do I do this correct? This thing's too nice. So 0 on y minus 1 over square root 2 and 1 on y plus. 1 on y plus is I over square root 2. Okay, so the number is actually nicer than I expected. I over square root 2. And it's an imaginary number, so it goes away, and the normalization should be just 2. Not very sure, but seems like non-square equal to 2, and so non should just be 1 over square root 2. Okay. And non should just be square root 2. Do I do this correct? I think so. Okay. Anyone finding any mistake in the calculation? Okay. Yeah. So okay, the norm is square root 2. And so, okay. And then we want to find the reduced density matrix. Okay. So psi is just this thing times 1 over square root 2, 1 over square root 2, that thing. Okay. So we can kind of forget the square root 2 for now. And so, okay. So now we want to find the reduced density matrix on A. Okay. And so we have, so we kind of have row AB equal to, well, we have the normalization vector 1 over square root, so 1 over 2, and this is psi tilde. And then we want to find row A, then row A equal to 1 over 2, then trans B, psi tilde. Okay? And yeah, so we want to find psi tilde, trace B. Okay? So what's this trace? So we want to find trace B, psi tilde, and I think we just need to do this brute force, okay? And that's so there are a lot of terms here, and that's trace B, and okay, so now things are ugly. So what do we have? Y minus y plus and 0, 1. So we have y minus y plus y minus y plus and y minus y plus and 0, 1 and 0, oh, wrong. 0, 1, y minus y plus, and 0, 1. 0, 1, and 0, 1. Okay, so we expand all the 4 terms because there are 2 terms, and we make into bra, and we multiply the bra with the cat, and turn all 4 terms. And it's really annoying now, so we need to do trace B, and that's like we take in 0, 0, and 1, 1 on the second register. Okay, kind of I tensor this thing, I tensor this thing. Okay, and so 0, 0, and so that's equal to. So let's see, 0, 0, and so 0. So 0, 0 on this, so we have so 0 on 1 plus is 1 over square root 2. So that's 1 over 2 y minus, and then 1, 1 on this thing. That's also 1 over 2. I think 1 over 2 is correct. Hopefully, y minus, y minus. Y minus, and then on this one, so 0, 0. Okay, so then we have plus. Okay, so this one is actually annoying. Okay, so on 0, because you have 1 here, is nothing, so only 1, 1. Okay, and 1 inner product is y plus is like 1 over square root 2y. Sorry, I over square root 2. And y minus 0. And on this thing, you have 1 here, so it's similar. 1 here, and but you have the complex conjugate of y plus, so y plus is, so that's a minus I over square root 2 of 0 y minus. And finally, is 1, 1 thing is plus 0, 0. And okay, let's see if we actually got the density matrix. So we have 1 times of y minus, so all those things adding together equal to 1 times, so 1 over 2 of, okay, so y minus, we can treat a little here. Y minus is this thing, and it's 1 to 1 minus I 1. And then we have, okay, so y minus 0. So I think this thing is just this thing, this thing and this thing are just dagger to each other. So let's calculate this thing too first. So that's I over 2 and 1I times 1, 0. And that's I over 2. And okay, so the 4 terms should be okay, should be 1, 0 and I 0, right? Okay, and this is a complex conjugate of it, so it's the same thing but I up here, and so that's which way should I write? I should write 1 over 2 and 2. Let's see, complex conjugate, so I up here, and but you should get a minus sign, and I minus I 0. Okay, and finally plus 0, 0, that's just 1, 0, 0, 0. Okay, and so the whole thing is okay. I think I don't need a 1 over 2. Oh, do I? So it's 1, 1, and okay. So it's 1.5 and 0.5 here, and Then we have this 1 over 2 circle to cancel out. It's minus I and I here. Okay. And yeah. And so it looks a Hermitian and it looks positive, and also its trace equal to 2. Okay, so the whole thing you divide this by another 2. Okay, so actually the number looks okay-ish. Okay, and well, okay. So about the calculation really hard because we are short on time, and we have like 30 minutes left. Okay, and yeah, so that's problem 5. And so problem 6 is really easy. Okay, so but some people still get it wrong. Please don't get this wrong. Okay. Actually, I should ask how do you actually get this wrong? But anyway, we have talked about how to find the leading order of those things, and we say polynomial are bigger than log. So this log 5 is not log n to the 5 is not important. What is important is those polynomial, and you want to find the leading order. So the leading order is n equal to 4 here, and is k is just 4 here. Okay. And okay, we are short on time, so let's skip the calculation here. We have 3 calculation here. I guess the most interesting one is this thing. So this thing actually we cheat a little bit because this is actually phase kickback. Although you can also do brute force calculation. So this thing is like a plus state, and so it's plus state here, and it's 1, and it's minus state here. And you can think about it's actually phase kickback on the plus state because you apply x on minus state, you get a -1 back, and if you don't apply x, then and obviously you don't apply x, then it doesn't happen. So it's you will be 0. It's like 0 tensor minus and plus. That's ignore 1 over square root 2 plus 1 tensor minus, and then you go through C naught, and it's still 0 minus here, and plus 1, and you got x on this minus, you get a minus sign, and a minus, so it's -1 on the minus, and so that's actually equal to minus. Okay, so that's C, and on A, B, you just need to do hard calculation, and I think something that we didn't do really nicely is I should emphasize that you should remember what's this thing. So that's this thing is control Z. Okay. So and that's the thing. If you write down the matrix, is 1, 1, 1 minus 1, and it's also CZ on AB equal to -1 to the AB. Okay. So it's like you apply Z on the second register if the first register is 1, but that also only do something when the second register is only 1, so you got a -1 when both the first register and the second register is 1 in computational basis. Okay, and also this thing is CCZ. Okay, CCZ, and what you do is you will turn ABC equal to -1 to the ABC. Okay, and okay, so where is our blank space? Let's try to go up. Okay, so let's do a proof of the S1 very first, and the last one. Okay, we have 10 minutes. We can do it. Okay. So the S1, so we want to say this XCCZ is equal to CCZ, X, and CZ. And what we do is we do this on computational basis state. Okay, so the first one is CCZ, and X on 1 on ABC. And so this is CCZ, and X on 1, so X will just turn this A equal to A plus 1, and BC. And this equal to, so -1 to the A plus 1 BC, A plus 1 BC. Okay, and so that thing is just equal to, now we do some algebra, so -1 to the ABC, and times -1 to the BC, a plus 1 BC. Okay, and so that's basically this thing. Okay, so the other one is x1 CZ23 and CCZ ABC, and that equal to x1 CZ and -1 to the ABC, and then the CZ give you this extra -1 to the BC, and this x1 take a equal to a plus 1, and so that equal to this thing. Okay, so that's this one. But obviously you can do more ugly thing. You can like check all 8 of them separately, etc. And okay, so we actually don't need to do 2 minutes on this thing. And the next one, if you know how to do it, is actually very fast. So what you do is you do streamy decomposition. Okay. So hopefully I spelled this correct. But yeah, you think about, so we say it's a pure state here. So it's important it's a pure state. It's a pure state, so you can do streaming decomposition on it. And think about what is streaming coefficient. Okay, actually only streaming coefficient is important. But there are only also some streaming basis. Okay. But anyway, so it's a 2-qubit pure state, and you think about what is streaming decomposition. So it's psi AB, and it should equal to some case, and both of them are two qubits. So actually, the streaming basis should be 2-dimensional, right? Because both of them are qubits. You only have so you only got so streaming basis is also normal basis. So you only got 2 of them. So you got this 0A. So you have, I guess let's use 1, 2, equal to lambda 1, 1A, and 1B, and plus lambda 2, and 2A, 2B. Okay. So streaming decomposition, you must look at this because this is also, so this 1A, 2A is some also no basis we don't know. And this 1B, 2B is some also no basis we don't know. Okay, but what we know is we know the reduced density matrix on A is 1/2I. Okay, and the reduced density matrix you read from here, that should be lambda 1 square, and this 1A, and plus lambda 2 square, 2A, 2A, right? And but this thing equal to 1/2I. And now you can compare the eigenvalues. And so 1/2I, the eigenvalues equal to, well, obviously 1/2, 1/2. And the eigenvalue here is actually lambda 1 square and lambda 2 square. So we are actually in a very degenerate case where this 1A and 2A, this 1B and 2A are arbitrary, because we have degeneracy between lambda 1 and lambda 2, and we have lambda 1 equal to lambda 2 equal to 1/√2. Okay, and once we know this, then the reduced density matrix on B will also become 1/2I pretty automatically. It's just because identity is identity in any basis. So we know the rho B equal to we need to find space. Let's see. Okay, maybe here. Okay, but rho B equal to, so the same thing is 1/2 this projector 1B, 1B, and 2B, 2B, right? But we know this 1 1B, 2B is also no basis. So this part is identity matrix, and so this is 1 and 2 times identity matrix. Yeah. So it's actually pretty easy if you know that if you are looking at stream decomposition. So it's very hard just because I'm hiding this. If I put this in hint, I think then people will know this. But yeah, and we try to do this a little harder. And anyway, we're actually seeing a lot of this state. So what is this state? Actually, the state is so this IP is this 1 verse square root 2, 1 verse square root 2. I've seen like a lot. So they are actually EPR pair. Okay, beta something. They are all similar. Okay, so like beta 00 will satisfy this. Okay, so we are seeing this a lot. So EX. So beta 00 is this 1 by square root 2 00 plus 1 1. So it satisfies reduced matrix is identity is total mix, and the reduced is total mix. And actually we also do this in homework, right? So like all the beta ij, so like beta 1 1. So all the different beta satisfy this. So basically you can take a beta 00 and then you change this 0 1 this 0 1 to any basis, and so you do local operation on those beta 00 and they all satisfy this relationship. So this thing is just beta 00 with some changeable basis on A and B. Okay. And yeah. Okay. Yeah. So that's problem 9. And 2 minutes, so I will stop trying to do the last two things in 2 minutes, but because we are out of space, but that's mostly about midterm. Any question? Otherwise, I think we can stop a bit early today, and we'll go back to our quantum algorithms on Thursday. Okay, so yeah, that's that's stuff now.